Yes, sir, you can start.
Okay, okay. So first, I'll quickly, 5 minutes, I quickly review what we have discussed in the previous session. Then we move on to the continuation of the session. Next topic. So what is a qubit? Formally, it is a basic unit of quantum information. And how do we formally define it? It has alpha ket 0 plus beta ket 1. What is the condition it has to satisfy? Mod alpha square plus mod beta square is 1. For example, in this case, 1 by root 2 ket 0 plus 1 by root 2 ket 1. Alpha is 1 by root 2, beta is 1 by root 2. Alpha square plus mod beta square is 1. In all these examples, like that. Okay. Now, if I go for measurement, in this case, alpha plus mod alpha square plus mod beta square is not equals to 1. Hence, these are not valid qubits. This quantum state representing as linear combination of ket 0 and ket 1. That only we say that it is existing in both states at the same time. That we call it as superposition state. Okay. These are all superposition states. Now, if we are talking about a system, let us say fan, electric fan, if it has 4 possibilities, what is ket medium? What is ket medium? This is the order we are following. Then what is ket medium? 0, 1, 0, 0. 0, 1, 0, 0. Similarly, ket low, ket high can be defined. So now, is it a valid quantum state? Yes. Why? Because mod 1 by root 2 square, mod 1 by root 4 square, 0 square plus 1 by root 4 square is 1. This we call it as superposition state. Superposition of all 4 possibilities. No. This is also superposition state. Here it is superposition of all possible 3 states. Okay, no? Linear combination or superposition. If you go for measurement, what happens? Ambiguity will go. We will get one of the classical states as outcome. Okay. If I measure system whose classical states are 0, 1, if I go for measurement, what are the possibilities we get?
0 and 1.
0 or 1. If it is heads or tails, we will get either heads or tails. Similarly, the other cases. So I measured a system whose classical states are heads or tails, and we got heads. Then how is it represented? Its state is represented. State is represented as 1, 0 or ket heads.
Ket 0.
If it is we are getting tails, then it is represented as 0, 1 or ket tails. Okay. Similarly, these cases. Now we can represent any 2-dimensional vector as a linear combination of these 2 vectors. Hence, we say that it forms a basis for 2 dimensions. Okay. For example, 1 by 5, 4 by 5, we can represent it as 1 by 5 into 1, 0 plus 4 by 5 into 0, 1. 1 by 5 into ket 0 plus ket 1. 4 by 5 into ket 1. Okay. Similarly, for 6 dimensions, for 6 dimensions, we have already seen. Okay. 1, 5 zeros, like that, total 6 vectors. Now, if we measure quantum state, which is alpha ket 0 plus beta ket 1, what are the possibilities of measurement? After measurement, we will get either 0 state or 1 state. What is the probability of getting 0? Mod alpha square. What is the probability of getting 1? Mod beta square. In this case, alpha is 1 by root 2, beta is also 1 by root 2. Hence, we got both as 1 by 2. Is that okay? Are any doubt in this? Here, probability of this is 8 by 9. It is 1 by 9. 1 by 9. Now, we stopped at this. If I measure this system, what is the probability of getting 3? What is the probability of getting 3? What is the probability of getting 3?
2 by 9.
2 by 9. 2 by 9.
2 by 9.
2 by 9. Next. Our next topic is quantum gates or quantum operations. Okay. Before understanding that, we need to understand what does a reversible operation mean. Reversible operation means, so all of us know what is NOT gate, no? Classical NOT gate. What is input and what is output? It is 1 bit gate, no, 1 bit. If 0 is input, output is 1. If 1 is input, output is 0. Is that correct? NOT gate. Now, if I tell you output, without any ambiguity, can you tell exactly what was the input given in this NOT case?
Yes, sir.
If I say that output is 0, can you tell me without any ambiguity what was the input?
Yes, sir.
Yes.
In general, for any operation, by looking at output, if you are able to determine what was the corresponding input, then we say that that operation is a reversible operation. From output to input, we are able to get back, no? Now you tell me, is this a reversible operation? Not operation? Is it reversible?
Yes.
Yes.
If I say that output is 1, without any confusion or ambiguity, you say that output is, input was only 0, no? State 0, no?
Yes, sir.
Similarly, in this case, if output is 0, input possibility is only 1. Hence, this is a reversible operation. What about this? This is input. Up to this, it is input. This is output. This is AND operation. Is it reversible or not?
No.
No, sir.
Well, here, if output is 1,
Only
we can tell
one.
what were the corresponding inputs. But if output is 0, we have 3 options. We don't know which is the correct input. Is that okay? Answer, is AND a reversible operation? No. What
No.
about this? What about this operation? What is this operation? You leave it for the time being. This is input, this is output. Is
Yes.
it a reversible operation?
Yes, sir.
Yes. If my output is 1, 1, what are the possibilities for input?
1 0.
Only 1 0. No other option is there, no? This kind of operation is called reversible operation. Okay, this name is C0. Later we will see. This is also a reversible operation. Now, what is our observation? In reversible operation, 2 inputs means 2 outputs. 1 input means 1 output. This is in general true also. In general true also. Now, tell me NOT and C0, are they reversible?
Yes, sir.
Yes. And
No.
no. What about OR operation? Is it reversible? Or
No.
are also not reversible operation. Okay. What is our observation? They have equal, reversible operations have equal number of inputs and equal number of outputs. Next, we try to understand all quantum operations are reversible and they are represented by some kind of matrices. To understand that, we need some terminology again. What is conjugate transpose of complex number? What is A plus IB conjugate? What is conjugate of A plus IB?
A minus IB.
A minus IB. We also know what is a transpose. Okay. What is conjugate transpose, also called as Hermitian transpose of a matrix? You take
Conjugate
transpose, you take
both.
transpose and conjugate each element in the matrix. Okay, let us discuss this. What is conjugate transpose of this matrix? First, you find out B transpose. What is B transpose?
1
1 plus I,
3 plus 2I.
3 plus 2I, 2 minus I,
4.
4. Okay. Next, what is the next thing that we need to do?
Transpose.
Conjugate, sir. What is conjugate of 1 plus I?
1
1 minus
1 minus I. What is conjugate of 3 plus 2I?
3
3
minus
minus
2i.
3 minus 2I. Conjugate of 4 is 4. Conjugate of 2 plus I, 2 minus I is 2 plus I. This is conjugate transpose. This is denoted by B dagger. Take transpose and conjugate each element. If it is a complex number, conjugate changes. If it is only real number, it remains like that. that correct? Is this conjugate transpose? Is that okay? Main diagonal doesn't change, only these two are interchanged. 2 minus I becomes 2 plus I, 3 plus 2I becomes 3 minus 2I, correct? No? This is conjugate transpose. Okay. Next, all quantum operations are reversible, that's what I mentioned, and they are represented by type of matrices called unitary matrices. Okay. Next one, what is unitary matrix? A square matrix U is said to be unitary. U times U dagger equals to U dagger times U equals to identity. We know what is U dagger now. After that, this is only matrix multiplication. Okay. Now, can you find what is, if U is 1001, what is U dagger? What is U dagger?
Same only.
Same only, because all are real numbers. Simply take transpose, that is enough. Transpose is again 1001 only. What is next step? U times U dagger. U times U dagger. That is 1001 into 1001. Is it identity? Yes. Hence, we say that this matrix is, other side also we need to calculate. This matrix is unitary. That means it is a valid quantum gate or quantum operation. That is the meaning. Okay. It is a valid quantum operation or quantum gate. Now, all these are valid quantum gates or quantum operations. And this is known as identity operation. Okay. This is very well known. This is called Harmod operation. Okay, that we will see. Oh, sorry. This is not identity. This is X. Quantum not operation. This is quantum not operation. Now, how to show that it is unitary? What is conjugate of transpose of this? 0I minus I 0. What is conjugate transpose of this? What is
0
conjugate
minus-
transpose?
Minus I 0.
Which is again the given matrix. Again, multiply this, we will get identity. Similarly, other side also identity. Hence, this is also valid quantum operation. Okay. Now, this is also valid quantum operation. The only difference is what is e power I theta? We know the formula now. It is cos theta plus I sin theta. You substitute this value and apply, then automatically this is also unitary operation. Is that okay? What is unitary matrix? A square matrix is unitary if U times U dagger equal to U dagger times U equals to identity. All quantum operations are represented by unitary matrices. Okay. These are all different quantum operations. 0, 1, 1, 0. Operation and gate I use interchangeably. Okay. 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 Now we'll see the first quantum gate, that is X gate. It is similar to or analogous to our NOT gate in classical computing. Okay. This is also known as poly X gate or simply X gate. Okay, by scientific name. Okay. It is a quantum equivalent of classical which gate? Classical NOT gate. NOT gate, what does it do? 0 to 1 and 1 to 0 it changes, no? 0 it changes to 1, 1 it changes to 0. Okay. Similarly, what is that you can expect quantum X gate to do? Ket 0 it changes to what?
Ket 1.
Ket 1. Similarly, Ket 1 to?
Ket 0.
Ket 0, as expected. And this is the matrix corresponding to that. 0, 1, 1, 0. 0, 1, 1, 0. Okay. And circuit for this is this. This is the quantum state. How X gate is a single qubit gate or a multi-qubit gate? NOT gate is single, it requires 1 bit as input or more than 1 bit as input. NOT gate, classical NOT gate.
1 bit only.
1 bit. Here quantum X gate, it requires how many? What? 1 qubit. 1 qubit as input. This is single qubit gate. This is single qubit gate. Is that okay? Quantum X gate is a single qubit gate. That means 1 qubit is input. That means, are these the only possibilities? Ket 0, ket 1? No, we have infinite number of options input. Not like NOT gate. NOT gate 0, 1 only input. But here quantum X gate, there any qubit is, it can be input, no. Okay. So special cases ket 0 input. Now you tell me what is the output here? What is the answer we get here?
Ket 1.
X gate we need to apply to ket 0. What is X gate? X gate means each gate is represented by matrix, no? This is the matrix. What is ket 0?
1
1
0.
0. If we multiply, we will get 0 1, which is nothing but ket 1. Oh, that means here the answer is ket 1. Are you getting?
Yes.
See, this is the representation of X gate. In box inside, we write X. This is the qubit. It is single qubit gate. It is the meaning. Okay, na? 1 qubit should be input. If ket 0 is...
Sir, you told that infinite possibilities are there.
I will come back to this, sir. First special cases, let me discuss. After this, we have that. Okay, na?
Okay, sir.
Okay. Ket 0 is input. Then output is ket 1. Ket 1. Now, this is called meter symbol. Meter means measurement. Meter means measurement. Now, if I go for measurement, what is that I get? Ket 1 I have. We can write ket 1 as 0 times ket 0 plus 1 times ket 1. No? Is that correct? Both are same or not?
Yes, sir.
Ket 1 is 0 times ket 0 plus 1 times ket 1. If I go for measurement, what is the probability of getting 0?
0.
0. What is the probability of getting 1?
1.
1. Here always 1 we get. That's all. That is 0 we never get. No, that is the meaning. Okay. Here similarly 1. Okay, let us discuss now. Now you tell me what is the answer here? What is the answer?
1. Ket 1.
How did we get this, sir? X on ket 0. Ket 0 is input. We are applying X gate. This is the input. And we are applying X gate to that. X gate means this is the matrix. Ket 0 means this is the matrix. We multiplied and we got ket 1. Here answer is ket 1. So if I go for measurement, what is the probability of getting 1? 1. What is the
1.
probability of getting 0? We never get 0. That means probability is 0. Is that okay? Is that okay? In this case, what is the answer? Input is ket 1. If I give ket 1 as input to quantum X gate, what is the answer we get?
Ket 0.
Ket 0. How did we get that, sir? It
1
is
into...
X of X gate we are applying to ket 1. We know what is the matrix for X gate, no? This is the matrix for X gate. We copy that. Ket 1 is
0.
the matrix is 0 1. Multiply this, we got 1 0. 1 0 is nothing but ket 0. Here the state is ket 0. Ket 0 we can write it as 1 into ket 0 plus 0 into ket 1. No? Is that correct? Now if I go for measurement, what is the probability of getting 0?
1.
1. What is the probability of getting 1?
0 never occurs.
We never get 0. That is the meaning. Sorry, we never get 1. Always 0 is the answer. Is that okay? After measurement, 0 is the answer. Total probability is 1. Now, so those who, someone has asked a doubt, no sir. Now I hope it will be clear. If alpha ket 0 plus beta ket 1, this is the qubit, no? General form of qubit. What is the condition it has to satisfy? Mod alpha square plus mod beta square. equals to 1. We can give infinite values for alpha, beta, where this condition is true, no, sir?
Yes, sir.
Yes.
Understood.
Now, exegate, if I use this kind of qubit, what is the answer we get? Exegate alpha ket 0 plus beta ket 1 is given. Beta ket 1 is given. Exegate alpha ket 0 plus beta ket 1. By linearity, what happens? Alpha is a constant outside, x on ket 0, here x on ket 1. Is that okay? What is x on ket 0? We have already calculated. What is x on ket 0?
Cat 1.
Ket 1. So it is x on ket 0 is ket 1, x on ket 1 is ket 0. Now substitute values in this. What is that we get? Alpha ket 1 plus beta ket 0. That means if alpha ket 0 plus beta ket 1 is input to quantum gate X, what is the output we will get? Beta ket 0 plus alpha ket 1 as the output. Is that okay?
Yes.
Is that okay?
Sir, can we say alpha ket 1 plus beta ket 0?
No, both are same addition only, no, sir. Anything is okay. Here it is written. No, both are equal.
Okay, sir. Thank you.
It is normal addition only, sir. Okay. Now, can you tell me what happens if ket 0 is given to X gate?
It became 1, sir.
It is 1 into ket 0 plus 0 into ket 1. No? If I give X gate ket 0, what happens? We observe that this 1 and 0 will be interchanged. That's all, no? It becomes 0 times ket 0 plus 1 times ket 1. 0 times ket 0 means 0, 1 times ket 1 is ket 1. Like this we get. Is that okay? These two are interchanged. Is that correct? Which is nothing but ket 1. Similarly, ket 1, we can write it like this. Are you getting any confusion here? Are you following?
Yes, sir. Yes, sir.
Yes, sir.
Okay. Alpha ket 0 plus beta ket 1. If we give this as input, what is the output? After applying X gate,
Is it ket 0? Is it ket 0, sir?
yes. Thank you, sir. Correct now? It is ket 0. Now, what is the output here?
Same. 1 by root 2 ket 1 plus 1 by root 2 ket 0.
Yes, sir. These two are interchanged. That's all. But both are 1 by root 2, no change. Same thing we get. Correct now? What about this in this case?
One by 3 ket 0 plus 2 plus 2 by 3 ket 1.
That's all, sir. In this case,
5 minus I by 3 ket 0 plus 3 plus I by 6 ket 1.
ket 1. Is that okay, sir? This is the way we get. Okay. Next, we will see some simple quantum circuits based on whatever knowledge we have. We have learned only one quantum gate, that is X gate. All other gate, the procedure is same, similar procedure, only matrix changes. That's all. Okay. Now, what is a resistor? We know what is a classical resistor. 16-bit resistor, we say. What does it mean?
Memory
It stores
space.
some bits of information, no?
Yes, sir.
Okay. Similarly, what is quantum resistor? It stores bits of information. It stores qubits of information. N qubit resistor means it can store n qubits of information. That is the meaning, no? Okay. Initially, all qubits are initialized to ket 0. Okay. This is the general form of quantum circuits. This is input. some quantum state here, some quantum states. Here we apply some operations like X gate we have seen, no? Like that, some gates we perform here, some operations. Then we will get some quantum state here, some quantum state as output. Okay, but this is quantum means we don't know which state it is in. So we go for measurement. Then we will get a classical result. It is either 0 or 1. Here it is either 0 or 1. Here it is 0 or 1. Is that okay? Input, we apply some quantum gates. Then we go for measurement. After that, we get output. This is the standard quantum gate circuit model. Okay. Now let us see one more quantum gate. Okay, now this is a quantum circuit. Here they applied X gate, Hadamard gate, UF gate, like this. Okay, this anyhow you will see as part of this. Okay, I think next session we have. This is called Deutsch algorithm circuit. This circuit anyhow they'll explain in detail. Okay. Now this is another quantum gate which is a single qubit gate, but most important gate. Most important gate. So what is the matrix for X gate? 0, 1, 1, 0. Similarly, here also it should have some matrix, no? Why this is 2 by 2 matrix? Why it is 2 by 2 matrix? It is single qubit. Qubit means 2 possibilities. That's why 2 by 2 matrix. Here also it is 2 by 2. 1 qubit gate. Single qubit gate means again it should be 2 by 2. Circuit is where X is there, that is X gate. H means H, Hadamard gate. Hadamard gate. Now can you calculate this and tell me what is the state here? What is the state here? Procedure is same. Now you are familiar with the procedure, no? Hadamard on ket 0. What is Hadamard on ket 0? What is the answer here? Same procedure.
Is it 1?
Sir?
Is it 1, sir?
Get one.
No. See, Hadamard on ket 0 means Hadamard, what is the matrix, sir? This is
1
the
by
matrix.
2. Yes.
This matrix you place here. What is ket 0? Ket 0 means 1, 0.
1,
After
0.
that you multiply both matrices. That's all, no?
Yes. Yes.
1 by root 2 plus 1 by root 2.
We will get a matrix as output, no, sir? Column. Okay, let us see this. This is the matrix for H. This is the matrix for ket 0. If you multiply 1 by root 2, 1 by root 2, we get. Can you write 1 by root 2, 1 by root 2 as 1 by root 2, 0 plus 1, 0, 1 by root 2?
Yes, sir. 1 by root 2 ket 0. Yes.
Again, 1 by root 2, I will take common, 1, 0. Here, 1 by root 2, I take common, I will get 0, 1. 1, 0 means it is?
1 by root 2 ket 0.
0, 1 means it is ket 1. That's
Yes.
what. This is also known as plus state. Okay? This is also known as plus state. That's what now we discussed. Any column matrix with the 2 entries, we can write it as linear combination of ket 0 and ket 1. No. Same, this column matrix again in terms of ket 0 and ket 1, we have written. That's all. This is called plus state. Now, can you tell me what is the answer? Is it superposition state?
Yes, sir.
Linear combination, linear combination of 0 and 1. That is called superposition. In fact, it is equal superposition. Why? Because what is the probability of getting 0?
1 by root 2. 1 by 2.
1 by 2. What is the probability of getting 1?
Same, sir. 1 by 2.
Same. That's why it is called equal superposition state. Okay. Okay. Now, what is the state here? Can everyone do it and tell me?
1 by root 2 ket 0 minus 1 by root 2 ket 1.
Thank you very much, sir. Same procedure. Only matrix is different. Okay. No. 1, 0, 0, 1, 1, 0 we have done for X gate. No, same procedure. What is the matrix here? This is the matrix. Multiply 1 by root 2 minus 1 by root 2. If you write it in this form, Simply, this becomes alpha, this becomes beta. That's all, no? Alpha ket 0 plus beta ket 1. Alpha is 1 by root 2, beta is minus 1 by root 2. This is called minus state. Is that okay? What is the probability of getting 0 if I go for measurement? Here the state is this. If I go for measurement, what is the probability of getting 0?
1 by 2.
What is the probability of getting 1?
Same 1 by 2.
1 by 2. But in the previous one also same, no? But this sign is important. Okay, that later you will understand in further lectures. This is called phase. Okay, that you will come to know later. Okay. Now, what is the output of the quantum circuit? This quantum circuit. We know what is H gate. We also know what is X gate. What is H? H is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2.
Minus 1 by root.
X is 0, 1, 1, 0.
1, 1, 0.
First you apply G. This is the order, left to right. Okay, no? First apply Hadamard gate. What is the state here? That is Hadamard on ket 0. Just now we have calculated now what is Hadamard on ket 0?
1 by root 2 ket 0 plus 1 by root 2 ket 1.
To ket 1. Thank you, sir. 1 by root 2 ket 0 plus 1 by root 2 ket 1. Now for this, what is which gate we need to apply?
Not X gate.
X gate. If I apply X gate to this also we have already seen, no?
Same answer.
It interchanges the coefficients, but still same answer we get. Okay, if you want, okay, to be more specific, T0, T1 like this. What is the state at T0? Ket 0 only. What is the state at T1? Hadamard gate on ket 0. Correct? Whatever state, what is the state at T2? Whatever state we got here at T1, for that we need to apply X gate. Is that correct?
Yes.
Now, what is Hadamard on ket 0? This is Hadamard on ket 0. Is that correct? This is 1 by root 2 ket 0 plus 1 by root 2 ket 1. Okay. Now, here this is the state. Next, what is that we need to do? X gate you need to apply to this. What is the answer?
Same.
Same. Only these two are interchanged now. Okay. Is that okay? How we got 1 by root 2 ket 1 plus 1 by root 2 ket 0, is that okay?
Yes,
Hello?
sir.
Okay, okay.
Yes, sir.
Okay. Now, for example, if instead of 0, if ket 1 is given, again we need to do from starting, no? Is that okay? Again we need to do from starting. Instead of that, directly what is that we can do is, we can find unitary matrix corresponding to all the gates here. Okay, what is unitary matrix here? First, which gate we are applying? Hadamard gate. Next, X gate. And here our input is there. Input, first X gate we apply, first one. Second one is X gate. Is this correct? Now, this action is given by, first you apply Hadamard and X. You find the product of these two matrices. Whatever you get, that is the resultant unitary matrix for this entire combination. Are you? Well, same circuit, second method we are discussing. Is the point clear? What is that we have done?
Sir, can you tell once again?
This is unitary matrix, sir. It is one operation. This is second operation. Two operations we have performed one after the other. Now, if I want to find single operation which represents these two operations, which is given by first we performed H operation, next we performed X operation. These two product you find out. That is the final unitary matrix corresponding to these two.
Okay, sir. Okay, sir.
Okay. What? Okay. Now, because this is product of unitary matrices is again unitary. Okay, this is unitary. Now, we know that this entire thing is equivalent to this matrix. Now, what is U on ket 0? What is ket 0? If ket 0 is input, what is the answer we get? U on ket 0. What is U? U means this matrix. Ket 0 means 1, 0. You multiply this. 1 by root 2, 1 by. It is same, no? Same answer we got no earlier also. What is the advantage? What is the advantage of this method?
Reducing two operations into single operation.
Yes. If input is different, no. So if, for example, ket 1 is given, no. Still, we need not calculate again. Already this matrix is available. What is that we can do? What is that we can do? Already this matrix we calculated and kept ready. This matrix is with us. Ket 1, directly you can apply this matrix. No, sir. This is the matrix. Ket 1 is 0, 1. You apply that, we get answer. Something like this. Okay. If we had applied first method, again, what is that we would have done? We would have applied a Hadamard here. Whatever we got, again, X gate here. If many gates are there, then this is easy, no? If possible to find this unitary matrix. Is that okay?
Yes, sir, got it.
Okay. Now, in general, one quantum state, that is qubit state, is given. How do you find this? It is of the form alpha ket 0 plus beta ket 1. Again, same procedure. We have got already matrix equivalent to this both, no? This is our matrix. This is of the form alpha ket 0 plus beta ket 1. Then we get alpha ket 0, beta ket 1 means we can write it as alpha beta, no? Is that correct? Alpha ket 0 plus beta ket 1, is it same as alpha beta?
Yes, yes.
Yes. Okay. Now we can directly apply alpha beta. After multiplication, whatever answer we get, that is the state here. That is the state here. It is only matrix multiplication only, sir. Once we know what are the different gates matrices, then it is only matrix multiplication and the Dirac notation. That's all. Okay. So is it clear using these two gates? What does this X gate do? Ket 0, it changes to ket 1. Ket 1, it changes to ket 0. How did we get that? 0, 1, 1, 0 is the matrix. If we use ket 0, that means it is X on ket 0. X is 0, 1, 1, 0. Ket 0 is 1, 0. Multiply, we'll get ket 1.
Ket 1.
Similarly, X on ket 1 means X is again 0, 1, 1, 0. 1 means 0, 1. Multiply, we get ket 0.
Ket 0.
Is that okay?
Okay, sir.
In general, any qubit is given, arbitrary qubit is given. What happens if you apply X gate? It interchanges the coefficients of ket 0 and ket 1. Correct, no? Alpha ket 0, beta ket 1 has become alpha ket 1 plus beta ket 0.
Wait.
Here what is the, after applying X gate to this, it becomes 1 by 3 ket 0 plus 2 plus 2i by 3 ket 1. They two got interchanged. Same procedure, Harmon gate. Only matrix is different. Procedure is dicto. Okay. What is X on Harmon on ket 0? Harmon means this is the matrix. Ket 0 is this is the matrix. Multiply, we will get 1 by root 2 ket 0 plus 1 by root 2 ket 1. This is called plus ket. Okay. Or equals superposition. What is Harmon on ket 1? We know what is Harmon, 1 by root 2, 1 by root 2. That ket 1 is 0, 1. Multiply, we will get 1 by root 2 ket 0 minus 1 by root 2 ket 1. So now, here one method is apply gates from left to right. This is one method of calculating the output. First, Harmon gate, if I apply Harmon on ket 0 is 1 by root 2 ket 0 plus 1 by root 2 ket 1. Next, to apply X gate. Next, to apply X gate. This is the answer we got. Okay. Again, interchange the coefficients. Same thing we get. If 1 is given, again we follow the same procedure. Harmon gate, we will get what? 1 by root 2 ket 0 minus 1 by root 2 ket 1. Again, interchange the coefficients here. But instead of that, if I give different input, again I need to apply from starting each gate. Instead of that, directly you can find a matrix equivalent to both gates. Okay, no? Both gates. First Harmon, next X. Harmon first, this is the first gate, this is the second gate. Find the product. It is going to be unitary. Then apply the input. Is the procedure, second procedure okay?
Yes, sir. It's okay.
Okay. Next one is, so far we talked about single qubit system. Now if you have two qubits, X is one system, but which is a qubit system. Qubit system means outcomes are 0, 1. Y is another system. This is also qubit system. Outcomes are 0, 1. What are the outcomes of this combined system? XY. What are the outcomes of this combined system XY? X first, Y next. See, X system can be either in 0 state or 1 state. Y system can be either in 0 state or 1 state. What are the outcomes of this combined system XY? X may be in 0 state.
0, 1, 1, 1.
Y also may be in 0 state. X may be in 0, Y may be 1. X may be 1, Y may be 0. X may be 1, Y may be 1. These 4 possible states, no? Is that okay? But here order is important. 0, 0, first to 0, next to this 0. Next to 0, 1 means first to this 0, next to this 1, like this. These are the outcomes of this combined system. How did we get this? Which is nothing but Cartesian product of these two sets. What is Cartesian product of 0, 1, 0, 1? 0, 0, 0, 1, 1, 0, 1, 1. Is that okay? In general, it is, this is the Cartesian product symbol. First set, Cartesian product, second set. Is that okay? Okay, this gate I will discuss after discussing other point. Okay. Now, for example, we have two systems. First system X, outcomes are 1, 2, 3. Second system Y, outcomes are 0, 1. What are the outcomes of this combined system? What are the outcomes of this combined system? Cartesian product of these two. First system 1, 2, 3. Second system 0, 1. Cartesian product 1, 0, 1, 1, 2, 0, 2, 1, 3, 0, 3, 1. These 6 states, no? Is that okay? Here order is important. Okay. Now, how do we represent ket 1 0? How to represent 1 0 or ket 1 0? How do we represent ket 1 0? 1 0 plus 1, remaining all are zeros. But it is a column. Column wise we need to take. How to represent ket 1 1? What is the column matrix equivalent to this? In this case, my system, these are the possibilities. Now, how to represent ket 1 1? Is this okay? This is one,
Yes,
1
sir.
0. Same procedure. Earlier we have discussed fan, PTech, CSCA, DSC, SIT, or die. Okay, same procedure. Now, because there are 6 outcomes, any unitary matrix corresponding to this, it should be 6 by 6 matrix. Why? Because there are 6 possible outcomes. 6 possible outcomes. This is one such unitary matrix. Now you tell me what is U on ket 1 1? How to calculate? U is this, ket 1 1 is this. Whatever we get, that is the resultant answer. Okay. What is U on ket 3 0? What is ket 3 0?
4 times 0, 1 0.
4 times 0 1 0. And after this, if you multiply, no. Answer is going to be 5 is in 1 is in 5th place. Answer will be 5th column. Answer is going to be 5th column. 5th column means 1 0, it is 0. This is the order now. 1 0, 1 1, 2 0, 2 1, 3 0, 3 1. Now 1 0 0, 0 1 1 1 0, 2 0 0, 2 1 1 by root 2. That means 1 by root 2 times ket 2 1 plus this also no. This is 1 by root 2 times ket 3 1. Is this okay?
Okay.
Got it, sir.
Okay, thank you, ma'am. Okay. So finally, what is the point you need to understand is how many outcomes are there? Any unitary matrix or operation on that or gate on that, its order is that much. Single qubit gate means how many outcomes? 2 outcomes. Single qubit means, that's why all single qubit gates are 2 by 2 matrices. If it is a 2 qubit gate, how many possible outcomes will be there in 2 qubit gate? 4. 4. All 2 qubit gates are 4 by 4 matrices. If I take any 3 qubit gate, it should be represented by which matrix? What type of matrix? What is the order of the matrix?
9 by 9?
No. 3 qubit means first qubit is 0 1, second qubit is 0 1, third qubit also 0 1. This Cartesian product, if I take, what is that? We will get 0 0 0, 0 0 1,
8 combinations.
0 1 0, 1 0 0, 1 0.
1.
1 1 0, all ones. 3 ones.
No, one more I will see.
Yes.
0 1 0 1 1. Okay, all 8. 8 possible. That means 3 qubit gate means it should be represented by 8 by 8 matrix. No? Single qubit gate means 2 by 2 matrix. 2 qubit gate means 4 by 4 matrix. 3 qubit gate means 8 by 8 matrix.
So 2 cube.
Now, Okay. For example, X is one system, Y is one system. I am performing operation U1 on X1. Independently, operation U2 I am performing on X2. What is the result of this combined operation on this combined system XY? It is given by U1 tensor product U2. Next, we understand what that tensor product means. Okay. Okay. Now, A is one matrix. This is, sorry, ket psi is one matrix. Ket pi is one matrix. Ket psi is another matrix. What is tensor product of these two? How do we calculate? Tensor product, ket pi, tensor product, ket psi. Now, ket pi, you write. What is ket pi? What is ket pi? AB, ket pi is AB. First matrix as it is, you write. Next, what you do is, next to each element of first matrix, you copy second matrix as it is. CD, here also CD. Is that okay? Is that okay?
Yes, sir.
Next, what you do is, you multiply all entries. A with C, AC, A with B, AD, B with C, BC, B with D, BD. This is the Cartesian product. Is that okay? Now, in this case, if it is 1 by 4, 3 by 4, 2 by 3, 1 by 3, what happens? 1 by 4, next to 2 by 3, 1 by 3, next to 3 by 4, 2 by 3, 1 by 3. 1 by 4 into 2 by 3, 1 by 4 into 1 by 3, 3 by 4 into 2 by 3, 3 by 4 into 1 by 3. Is that okay? Is this example clear or any doubt?
No doubt, sir.
No,
Yes, sir.
In this case, what is tensor product? Can you tell me? Can someone tell me?
Six, sir.
V1, W1.
Hmm.
Yes.
Next row, V1, W2.
V1, W3. V2,
Yes,
W1, V2, W2, V2.
Wait with
Is
W.
this same thing, no, madam?
Yes, sir. Yes, sir.
Okay. Okay, thank you. In general, what is tensor product of these two?
Alpha 1, beta
Alpha
1
1,
plus alpha 2, beta 2 plus
till
alpha 1,
beta
alpha
k.
m, beta k.
Alpha 1,
M,
beta
beta
k. Next, alpha 2, beta 1, alpha 2, beta 2, and so on, alpha 2, beta k, and so on, alpha m, beta 1. Is that okay? Up to this alpha 1 over, alpha 2 over, next alpha 3, like that, last one, alpha m. Is this okay?
Okay.
Now, this is a Hadamard with Hadamard tensor product. This is Hadamard. This is Hadamard. Again, this is also Hadamard. This is the tensor product. How did we get this? 1 by root 2. Okay. 1 by root 2. You copy next to this entire matrix you copy.
1 by 2, 1 by 2.
1 by root 2, 1 by root 2, minus 1 by root 2.
1
Again,
by 2.
This 1 by root 2 you take, that entire matrix you copy. Next to 1 by root 2 you take entire matrix. Next to minus 1 by root 2, entire matrix. Is that okay? Is that okay?
Yes, sir. Yes, sir.
So 1 by root 2 into 1 by root 2, 1 by 2. 1 by root 2 into 1 by root 2, 1 by 2. 1 by root 2 into 1 by root 2, 1 by 2. 1 by root 2 into minus 1 by root 2, minus 1 by 2. So first two 4 entries are 1 by 2, 1 by 2, 1 by 2, minus 1 by 2. What are next to 4 entries? Same thing, no? Next to 4 entries also same thing. Next to 4 entries, only minus sign is different. Minus 1 by 2, minus 1 by 2, minus 1 by 2, 1 by 2. Is that okay? One by 2, if you take common, if you see here, see 1 by root 2, 1 by root 2, 1 by 2. First two 3 elements, they are same. That's why this here we get the same thing. Here it is minus x, minus sign different. Plus 1 becomes minus 1, minus 1 becomes plus 1. That's why this. Is it clear or any doubt in this?
No, sir, it is clear.
Yes, sir. Clear.
Tensor product is
Okay.
very clear, sir.
Okay, thank you. Now, I am talking about two systems. First system, I am not performing any operation. Second system, I am performing Harmod operation. What is the combined action? What is the combined action? Not performing anything is performing identity. Second one, Harmod. Identity, tensor, Harmod. Identity, tensor, Harmod. Again, you can calculate this. Okay. Next. Okay. Now, let us see. Again, first we will discuss this, next we move on to that. Okay. We are given a quantum state like this. Is it a valid quantum state of 2-qubit state? X is a qubit, Y is a qubit system, XY is a 2-qubit system. Is it valid 2-qubit state? X outcomes are 0, 1. Y outcomes are 0, 1. What are the outcomes of XY? 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0. Only these combinations are there. No? Hence, outcomes are okay. Now, what is the next condition we need to check? What is the next condition we need to check?
Mod 1 by 2 square plus
Mod 1 by 2 square plus mod I by 2 square plus mod minus 1 by 2 square plus mod minus I by 2 square. Is it 1? All are 1 by 4, no? 1 by 4 plus 1 by 4. Plus, it is finally what is given to us is 1 by 2, I by 2, minus 1 by 2, minus I by 2. Is it a valid quantum state or not? We are checking.
yes, sir.
There are 4 entries. Why? Because it is a 2-qubit system. Okay. Is that okay? Okay. Now, how do you represent ket 0, 0? Ket 0, 0. See, this is 0. Order is 0, 0, 0, 1, 1, 0, 1, 1. How do we represent ket 0, 0? 1 followed by. This is our order, no? 0, 0, 0, 1, 1, 0. What is ket 0, 1?
0, 1, 0, 0.
Similarly, what is ket 1, 0? Third one.
0, 0, 1.
What is ket 1, 1? Is that okay? Is that okay?
Yes, sir. Yes.
Now, first of all, how did we get this? Ket 0, 0. Ket 0, 0 means it is same as ket 0 tensor ket 0. What is ket 0? 1 0 tensor. What is again ket 0? 1 0, which is 1 1 0 0 1 0. Is it same as 1 into 1? 1
1 0
1
0
into
0.
0
One all
0 into 1 0 0 into 0 0. Is this okay?
Yes, sir.
This is the one we got now. That means ket 0 0 we can write like this, or ket 0 tensor ket 0. This is also correct. Or simply some people, some textbooks, some places they write ket 0 ket 0. This is also correct. Okay. Are you following, or any confusion here?
No, sir, we are following.
Okay, okay, thank you. Now we are given a quantum state like this. Okay, we are given a quantum state like this. Now, but it is a 2-qubit system. Can you represent this pi quantum state of 2-qubit system as tensor products of quantum states of first system and quantum state of second system? Is it possible or not? Is it possible or not? Let us see here. This entire state, what is this? This is 1 by 2, as we discussed earlier, I by 2 minus 1 by 2 minus I by 2. This is our state now. This is our state. Can we write it as like this? What is this? 1 by root 2
1 by
minus
root 2
1 by root 2. First system. Second system, 1 by root 2 I by root 2. Whether both are same or not. Both are same or not.
Yes, sir.
If at all we are able to write it like this, then we say that this system, they are independent. They are independent. And this state is called product state. That means if I make some changes here, nothing will happen here. They are independent. One is not going to affect the other one. Okay, this is called product state. Is that okay? Is it product state or not? Yes. What about this? Is it product state or not? In this case, it is impossible to write this as first system state tensor product second system state. Why? Because okay, we don't know what is first system state. Let us call it as ket psi 1. First system state. Let us call this as alpha ket 0 plus beta ket 1. This we can write it as alpha beta. Second system state, that we don't know. This let us call it as gamma ket 0 plus delta ket 1. This can be written as gamma delta. Is that okay? Is that okay? If at all it is possible to write it as tensor product of these two. If pi is say equals to ket psi 1 tensor ket psi 2, then what should happen? What is psi 1? Alpha beta. What is psi 2? Gamma delta. What is this value? Alpha gamma. Alpha.
beta,
Sorry. Alpha gamma. Alpha delta. Beta gamma. Beta delta. Is that okay? This is 0 0 1. This is 0 1. This is 1 0. This is 1 1. Okay. If ket pi is this, what is ket pi? Ket pi I can also write it as 1 by root 2, 0 0 part, 0 1 not there, 1 0 not there, 1 1 it is 1 by root 2. This both values must be equal, no? Both values must be equal. That means alpha gamma is how much? 1 by root 2. Alpha delta is how much? 0.
0.
Alpha delta equals to 0. Then when does it alpha delta become 0? Alpha is one number, delta is another number. When does their product become 0?
If any one,
Either alpha or delta must be 0.
If alpha is 0, then what happens? Here, if you see here, if alpha is 0, alpha gamma should become how much? 1 by 2, 1 by root 2. Is it possible? If
No.
alpha 0, alpha gamma product must be 1 by root 2. It is impossible.
yes,
See, alpha gamma is 0 means one possibility is alpha equal to 0. If alpha is 0, alpha gamma should become 1 by root 2. It is impossible. Hence, alpha is 0, not possible. Let us take delta is 0. If delta is 0,
not
then
possible.
what is beta delta value must be equal to 1 by root 2. Is it possible? Delta 0 is also not possible. But alpha 0 is not possible. Alpha is not equal to 0. Delta not equal to 0. Then how alpha delta equal to 0? This is impossible. That means what? It is not possible to write this state as product of two respective system, tensor product of respective system states. That means this is not a product state. That means both states are not independent. If I make some change here, something will happen here. If I make some change here, something will happen here. Okay? If I make some changes to X state, automatically Y state is going to be changed. That means there is some kind of correlation between them. That means they are not independent. And that type of state is called entangled state. Entangled means there is some kind of relationship between both the two. In this case, is it clear why they are entangled? Because they are not independent. They are not independent means they are called entangled state. Now I think you can read this. Okay. We are not able to write it like this in the second case. That's why this we say that they are not independent. They are not independent. And that state is not a product state. The product state which is not a product state is called entangled state. Is called entangled state. Now, these are all entangled states. These are also examples for entangled states. These are all examples for entangled state. But is it entangled state? No. I can write it as ket 0, tensor ket 0, tensor ket 1. Okay. This is not entangled state. And this is one of the Bell states. Like this, there are 3 other states. Okay. This is called Bell state. All Bell states, they are entangled states. And this entangled state is starting point in many other quantum algorithms and protocols. Okay? Quantum protocols. These are all, you can check whether these are entangled or not. Is it entangled? Is it entangled?
Yes, sir. Yes, sir.
No. Why?
Yes, sir.
Because in the 3 systems, 3 qubit system, I am able to write it as individual systems product, no tensor product. Hence, this is not entangled. This is simply product state. This is simply a product state. Okay. Now, how do you find output of the quantum circuit like this? Now, this is first system. This is say second one, X and Y. Independently, we are performing some operations. Here add mod, here add mod. What is the combined action? What is the combined action? Add mod, tensor, Hadamard. This gate we don't know. Okay, this I will explain in next 2 minutes. Again, what is this action? Hadamard, tensor Hadamard. And this is called C0 gate. Okay. This is a 2-qubit gate. 2-qubit gate means matrix must be 4x4 matrix. This is a 4x4 matrix. Here what happens is, this is called control, this is target in the input. Similarly, output also same thing, control target. Here what happens is, if control is 1, target is flipped in the output. Here control is 0. Whether target will be changed? No. Whatever is input, same thing we will get as output. Here control is 0. Whether target will be changed? No. Same thing we will get as output. Here control is 1. Target becomes 0 becomes 0 becomes 0 becomes 0 becomes
1.
1. That's why 1 1 is the output. Here target is control is 1. So that's why this target becomes 1
0.
becomes 0. That's why 1 0 is the output. Is it okay? Or first column is same as third column. Control as it is. Target how we get is, it is XOR of inputs. 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. Is that okay? If control is 1, target is flipped. Control target. Are you getting any confusion?
No, sir.
Okay. And this is a circuit for this. This is called control. This is target. Target is XOR. XOR means this XOR is the result. No, that's why this symbol. Okay. This is the matrix. Now can you quickly tell me what is this? What is input here? This is 2 qubits. No, 2 qubits are input. Ket 0, another ket 0. This is given by ket 0 tensor ket 0, which is same as ket 0 0. What is ket 0 0? 1 0 0. No, we have already discussed. No. Now, if ket 0 0 is given as input to 2 qubit gate C0, what is the output? You write C0 matrix. Ket 0 0 is this value. After that, multiply. This is C0 matrix. Ket 0 is this. Multiply. What is that we get? First column of 1 is in the first place. That's why first column we will get as output, which is same as again ket 0 0. Are you same procedure? C0 on 1 0. First write C0 matrix. C0 matrix is this. 1 0 is what is the matrix for 1 0?
0 0 1 0.
This is the matrix for 1 0. You write that, we will get 1 1. Is that okay? That is C0 matrix. This is 2 qubit gate. Now this is nothing but our C0 now. Now what is the action? First this we need to apply. This is Hadamard, tensor Hadamard. After that, next which gate? Second gate is this. This is first one, this is third one. This is first one, second one is C0. Again, third one is Hadamard, tensor Hadamard. This is the order we apply. Finally, we will get single unitary matrix. Single unitary matrix corresponding to this. The entire thing you calculate, you will get one unitary matrix like this. After that, what is this? 0 0. 0 0 I apply. 0 0 is, this is the matrix. Apply, then we will get 0. Oh, this entire thing is going to give us only this much. Like this, you can practice some examples. Okay, these are different. Okay. And then you can also calculate what is Hadamard on ket 0. This we have already done. What is Hadamard tensor 2 on ket 0 0? This is Hadamard tensor Hadamard. Hadamard tensor Hadamard matrix is this. Ket 0, 0 is this. Then we will get something like this. What is this? All possibilities with 1 by 2. 1 by 2. This is equal superposition state. Equal. And this is the starting point in many algorithms. Next, there are some quantum algorithms. They are going to use this. Okay. All 4 probabilities. Probability is root 2 whole square. The coefficient is root 2 whole square. We will get 0, 0 with probability 1 by 4, 0, 1 with 1 by 4, 1, 0 with 1 by 4, 1, 1 also with 1 by 4. Here, what is the answer? Can you tell me? Hadamard tensor 3, kept 0, 0. All 8 possibilities we will get with the probability 1 by 8. 1 by 8 means here 1 by 2 root 2 should be there. Similarly here. Okay. So finally, what is that we have discussed? We have seen what is quantum computing. Okay. Next, why quantum computing? Why quantum computing? Next, we have seen fundamentals of quantum computing, like what is qubit? What is qubit? Next, what does measurement mean? Next, what is superposition? Okay. Next, we discuss what are reversible operations, unitary operations, quantum gates, and mainly I talk about X gate, H gate, and C0 gate. Procedure is same. Okay, the procedure is same. Only Y gate and Z gate matrices are different. That's all. Okay. This is single qubit. This is 2 qubit gate. Next, to quantum circuits. Okay, these are the references. This is standard textbook. And I request you to please go through this website. And if you are new to the area, you can start reading from this. It is neatly explained, very well explained. It is easy to follow also. Once you get some kind of familiarity, then you can start reading this book. And this is one link, YouTube link, where they have explained entire quantum computing in less than 2 hours very neatly. Okay. You may use that. Thank you very much. And
Thank you, sir.
I once again thank the coordinators for giving me an opportunity to be part of this online activity.
Sir, thank you so much.
Thank you very
sir.
much, sir. We have a nice session, and you start the first day itself. We have started very nicely. I request any of the participants to give feedback, at least 1 or 2.
Sir, can I?
Oh, yeah, definitely. Please introduce yourself and you can give.
Yeah, myself, Dr. R. Venkateswara from Reddy Institute of Engineering and Technology, Vizianagaram. Dr. P.V. Subba, sir, thank you so much, sir. You made it very clear, and we learned a lot from A to Z, sir, regarding the fundamentals of quantum computers. Thank you so much. Because even layman can also easily understand. You taught in such a manner that peeled that banana and spooned it and eat it, sir. So much. Thank you so much, sir.
Thank you, sir. Thank you very much for being interactive. Okay.
Yes, sir. That itself is very clear, sir. Creating a lot of interest regarding this quantum computing. Thank you so much, sir. And we must also thank to our organizers, Dr. Murthy Garu, for the nice and wonderful platform created. We must also thanks to ATAL platform. Thank you so much, sir.
Thank you. Any one more? Any one more, sir?
The session is very much informative and very clearly explained. I attended other FDPs, but in this FDP, the explanation is so clear and lucid.
Thank you, sir. Thank you very much for kind words. Okay.
Thank you, sir.
And it is also more interactive, sir. That's why it is lively, sir. You allowed us to interact at all times, sir. Thank you so much, sir.
Thank you very much, sir. Subba Reddy, sir.
Thank you, sir. Thank you, sir.
Sir,
Thank you.
sir, Murthy, sir.
Yeah.
Yeah,
Please.
can you share the PPT and video, sir? Because
Definitely, sir.
this much valuable video and PPT, we won't get, I think. Please share it to.
100%, sir. We are uploading in YouTube.
Sure,
So
sure.
the moment I will get the PPT also, I will share with all of you. I have already shared the feedback form for both sessions. I made it one only because both are taken by same Subba Reddy, sir. Thank you. Thank you very much.
Thank you. Thank you, Subba Reddy, sir.
Thank you, sir. Thank you very much.
बस इतना सामान है मार्केट से और कुछ इस तरह का पनीर मसाला टिक्का बन जाएगा तो ये काफी जल्दी बन जाता है इसलिए कौन सा पौधा है कि उसको बस इतना सामान है मार्केट से और कुछ इस तरह का